Good afternoon. My name is Ravi Babu, Assistant Professor in Triple Department. Today we are going to sing in second module, that is system response. In system response, today we are going to sing inverse jet transform by residue method and direct division method. In yesterday class, we will see the inverse jet transform in case of the partial fraction method. Now we are going to sing now inverse jet transform by residue method and direct division method, where in case of the residue method, the inverse jet transform is going to be defined as, if you know the x of k is analog signal or digital signal, anything, if you convert that one into jet transform, that is for analyzing purpose, it is coming to as x of z. So in case of residual form, it will be x of k equal to sigma I equal to 1 to n residue of x of z into z power of k minus 1 at pole pa. That is nothing but in any system you are having the in denominator part you are having the poles. That is in that poles at the origin of circle you are taking the each poles we are going to be residue. Whereas in case of the fractional fraction method and comparing the problem with residue method, it is getting same answers, same problem solutions. Okay, but the convention for calculating of inverse jet transform method is different in case of the residual and fractional fraction methods. That is, in case of the residual method, if you take, always we are going to be analyzing with the poles of the system. At particular poles, we are going to be taking the each one residuals. That is, for every poles, we are going to be taking the residuals. After that one, you find the inverse jet transform. That is, we are taking the residue of x of z in the form of the x of k is in the form of the x of z into z power of k minus 1. So, for disciplinary poles, that is, if you take any pole, here I am taking the Ri. So, Ri is the particular pole. I am taking the particular pole Ri. For that one, the residue of x of z in terms of the z into k minus 1 is residue of x of z power of k minus 1 for particular pole p I. Z is nothing but at particular pole there is pi. So for that one, we are taking the formula as limit. We have to apply for that one limit where the z value is going to be taking as the pole value, that is pi into zpi into x of z power of k minus 1. It is in case of the distinct poles. Okay, in case of the distinct poles, if the poles are repeated, that is nothing but multiple poles. Here I am taking the n times of the poles. For example, if you have any pole is going to be repeated, in that case, the residue of x of z into z power of k minus 1. For this one, the value is coming to as r equal to. So here I am taking the residue value is capital R. Whereas the distinct poles, I am taking the residue value is Ri. Where here in repeated poles, I am taking as R value. R equal to 1 by n minus 1 limit z stands to pi. Derivative of n minus 1 by derivative of z times n minus 1, where z minus pi whole power of n into x of z into z power of k minus 1. So for this one, we are taking the residue of for repeated poles for this formula. So I am taking the one of the example here. Let consider x of z equal to 1 by z plus z power of n into z plus 2. Z plus 2. So first of all, I am taking the residue of x of z into z minus k. For that one, at pole of z equal to minus 1. Z equal to minus 1. But here n power of n will be there. That is nothing but here denominator part is called as a poles, no? So denominator part is called as a poles. So here z plus 1 power of n, that is nothing but here n terms of poles are repeated. So what is the for that in terms of the poles for formula is 1 by n minus 1. So 1 by n minus 1 factorial limit distance to here the value is pi value is 1. So 1 distance to minus 1 first pole. So d power of n minus 1 into d power of n minus 1, and that function is nothing but it is z plus 1 whole power of n into x of z into k power of n minus 1. If you apply this one for calculation part, that is if you taking this one here, what happened? The limit of the derivative of this one is 1 by z plus 1 into z power of k minus 1 is coming. Okay, so if you taking that, this is the for residue of first term, that is z plus 1 whole power of n terms. Z plus 1 whole power of n terms for residual, it is residual. Coming for the next one, if you take the second term, that is z plus 2, that is z plus 2. If you taking for z plus 2, if for this z plus 2 residual, that is nothing but it is a single pole, no? What is the pole value here? That is z equal to minus 2. Z equal to minus 2. Z equal to minus 2. So residue of x of z into z power of k minus 1 at z equal to minus 2 is, that is, it is formula. This is a formula. It is not a repeated pole, no? It is a not repeated pole. So this is the formula. If you repeat a pole, nothing but if you take this formula right here. Okay. So r equal to limit distance to minus infinity. So what is the 0? What is the pole value here? Z equal to minus 2, no? So distance to minus infinity, z plus 2 zpi into 1 by z plus 1 whole power of n into z plus 2. Okay. So it is z power of k minus 1. Z power of k minus 1. If you taking the limits up in this one, here z power of k minus 1 and z plus 1 will be there. So if you take limit z distance to minus 2, if you substituting this one, the value is coming to us here. This z plus 2 is cancelled and this z plus 2 is cancelled. So what happened? Only z power of k minus 1 by z plus 1 whole power of n is possible. So it is the residue of the second part. So after adding these derivative values, we are get the inverse Z transform. This is the way we are going to in residue method for applying the residue method for the Z transform. Z transform. Now I am going to the one of the problem, that is if you take inverse Z transform of x of z equal to z plus 2 by z plus 1 into z plus 3. Already we see this one in case of the fractional fraction method. Okay, partial fraction method. Same problem, you will see the partial fraction method. You are getting the same answer here, this one. Now I am going to for this one is with respect to residue method. Residue method. So when you are going to for starting the residue method, first of all, in your system, identify the number of poles. Poles nothing but in a system, the denominator values equal to 0, nothing but that is the poles. Here it will be z plus 1 will be there. That is nothing but z plus 1 equal to 0, z plus 1 equal to 0, that is z equal to minus 1. Z equal to minus 1 is the one of the pole, and z plus 2 equal to z plus 3 equal to 0, that is z equal to minus 3. It is the one of the one of the poles. One of the poles. So for z equal to minus 1 and for z equal to minus 3, we are going to finding the residuals. Residual. Okay, residue method. So for that one, I am taking first of all residue of first one, that is z equal to minus 1. Z equal to minus 1, I am going to taking the first of all that one. So in case of the z equal to minus 1, residual nothing but it is limit distance to r1 equal to, so I am already representing here R1 equal to limit z tends to minus 1, and what is the pole that one? For this one, we will first term no. So that is z plus 1 into total function, that is z into z plus 2 by z plus 1 into z plus 3 into z power of k minus 1. It is for dissipative poles. Okay, it is not a repetitive pole, no. It is only dissipative pole. That is z equal to minus 1. It is a formula. If you substitute this one here, so here z plus 1 and z plus 1 is cancelled. Only z plus and z is minus 1. Substitute this one values, and it is z into z power of k minus 1. That is nothing but it is coming to as z power of z only. Z only. So final of calculation of this one, that is getting here z into z plus 3 by z into z plus 2 by z plus 3. Okay, z power of k into z plus 2 by z plus 3. So if you substitute the limit value here, so it is coming to as minus 1 plus 1 by minus 1 plus 3. Okay, for this one it is z equal to minus 1, no, sorry, minus 1 plus 2 into minus 1 all power of k by minus 1 plus 3. So this value is minus 1 into minus 1 of k by 2. So if you are getting this one is, that is value is 0.5 into z power of, sorry, 0.5 into minus 1 power of k. It is for the restrictive poles for residual value for first one. Coming for the second one, that is the pole of the p equal to minus 3. P equal to minus 3. For that one, we are going to find residual method, that is R3. R3, where limit z tends to 0. First you have to write down the what is the value of this pole value, that is this form z plus 3. Okay, z plus 3. After that one, we have to write down the total function. After that one, residue is for only for in the terms of the k minus terms. So z power of k minus 1. So here, so z plus 3 and this z plus 3 is cancelled. So after that one, for calculating of this one, we are getting here z power of k minus 1 is there in the denominator value, and z will be there. That is nothing but z is coming. So z plus 2 by z plus 1. We are getting z plus 2 by z plus 1. Into z power of k. Substitute the limits values. That is z equal to how much value? The second pole is minus 3. Z equal to minus 3. That is the second pole. Substitute this value into here. So minus z equal to minus 3 now. Minus 3 plus 1 nothing but minus 2. Okay, into minus 1 whole power of minus 3 whole power of k. So minus 1 into minus 3 whole power of k by minus 3 plus 1, that is minus 2. For this one solution, we are getting 0.5 minus 3 whole power of k we are getting. After adding these two, we are getting here 0.5 whole power of minus 1k, 0.5 whole power of minus 3k. So it is the inverse transform of this function, given function, by using residue method. This is the final answer. Now already we see same problem in fractional fraction method. Okay, once again I am repeating for this one fractional fraction method. In case of the fractional fraction method, first of all, the given function is x of z by z formation. Always the function is in the form of, in case of the fractional fraction method, x of z by z formation. So what am I the function? Actually it is z into z plus 2 by z plus 1 into z plus 3. But when we are going to fractional fraction method, I am going to verifying with fractional fraction method, same problem. So when we are going to fractional fraction method, the function is of the function RHS LHS side will be in the form of x of z by z. That's why in a function I am taking this one is in here, in this way LHS side. The z will be going to be from RHS to LHS side. So it is coming to as denominator. So it is coming to as fractional fraction LHS side standard formation. So what is the form? What is the RHS side will be there? That is z plus 2 by z plus 1 into z plus 3. If you take for this one fractional fraction, that is nothing but here we are having the two variables. That is, in the denominator, two poles will be there. Similarly, here we are having the in denominator two variables. That is, first variable is z plus 1. Okay, for this one, the value is constant number is a. Plus, the second variable is b by z plus 3. B by z plus 3. If you want to a value here, a equal to, first of all, here total function you have to write z plus 2 by z plus 1 into z plus 3 into what is the value of the a in the denominator value? That is z plus 1. In denominator value of the a is z plus 1 here. Z plus 1. So multiply with z plus 1 and where substitute the value z plus 1 equal to 0, that equal to z equal to minus 1 here in this function. So for here this is this one and z plus 1, this one cancel. Substitute these values, z equal to minus 1. So it is 1 by z equal to minus 1, 2. That equal to a equal to the how much value? 0.5. A equal to 0.5. Similarly for b. So I am going for the next one is b value. A is 0.5. Remember that one. If you want to b value here, first of all you have to write out the total function. That is same process, z plus 1 into z plus 3, and the total function is multiply with what is the value denominator of the b value is z plus 3. So multiply with z plus 3 and substitute the z values. That is nothing but the denominator value of z value is nothing but equal to 0. That is, I am representing here z equal to minus 3. Calculate this one. Z plus 3 cancel. Z equal to minus 3 nothing but in numerator value it is minus 1. In denominator value it is minus 2. That is nothing but we are getting here 0.5. So in previous one the same way 0.5. Here also 0.5. Substitute these values into here in a function. It is, so what is x of z by z value equal to a value is 0.5. No, that is nothing but 0.5 by z plus 1 plus b by b value is 0.5 by z plus 3. 0.5 by z plus 3. Okay, after that one, here LHS side we take the z now, going to take the from RH side, that is x of z equal to 0.5 z by z plus 1 plus 0.5 z by z plus 1. Okay, z by z plus 1. Now I am going to convert this into, applying the inverse Laplace transform. That is, it is coming to as x of k equal to, generally for this one the formula is, if you have a of k is there, for applying for this one z transform you get that one is, that is z by z minus a. So here z plus 1 will be there, so that's why it is 0.5 into minus 1 over power of k plus again 0.5 into minus 1. What is the value of this one? B. 0.5 no? 0.5 into what is the value? Sorry, here 3 no? The B, second pole, z plus 3. So it is minus 3 whole power of k. So it is fraction method. Partial fraction method, it is same. Whereas compare this one to residual method. We are getting same answer, no? Okay, it is one of the method. Okay, inverse of z transform by using residue method. Okay, here we are going to be comparing is equal. Now I am going to another problem. Okay, we got the same answer in case of the partial fraction method and inverse z transform method. Sorry, partial fraction method in finding the inverse z transform in case of the partial fraction method and residue method. Now I am going to another problem, that is z by z plus 1 into z plus 2 whole square. That is, here we are getting the multiple poles. First of all, identify the poles. So first of all, identify the poles. That is nothing but in a given function denominator value is equal to 0. That is Z equal to minus 1 is another pole, and Z equal to minus 2 comma minus 2. Repeated poles. Square terms with repeated poles. So find out the first part, residue what? Residue of x of k. Residue of x of k. That is nothing but residue of x of z into k power of minus 1. For that one, it is a disciplinary false no. That's why we are getting here R1. R1, that is limit z times 2. It is a value of first pole no, that is z equal to minus 1. Z equal to minus 1. Z equal to minus 1. Z power of, so z limit z tends to minus 1. Okay. Into which value are taking? First pole no. First pole nothing but that is z plus 1 into z plus 1. Limit z tends to minus 1 into z plus 1 into total function z by z plus 1 into z plus 2 whole square into and residue formation, that is z power of k minus 1. K minus 1. After that one, here we are getting here z plus 1 and z plus 1 is cancelled. Z plus 1 and z plus 1 is cancelled. And here z will be there. Here z power of k minus 1. That is nothing but we are getting z power of k only. Z power of k. Z power of k. Z power of k. And numerator value is z plus 2 whole square. Z plus 2 whole square. So up to z equal to minus 1 here. So minus 1 whole power of k and plus 1. So it is coming to as minus 1 of k. Minus 1 of k. Okay. Coming for that one, next one is residue of second pole. What is the second pole? That is z plus 2 whole square. Z plus 2 whole square nothing but it is a repeated pole at minus 2. It is a repeated pole at minus 2. So what is the formula for this one? For this one, we are having the standard formula is 1 by n minus 1. And nothing but x for z square no, it is n. It is n. It is n. So 1 by 2 minus 1 factorial limit z tends to infinity. Sorry, z tends to what is the value here? Z equal to minus 2. Z equal to minus 2 d by dz of the denominator of the second pole value, that is this one, denominator of the second pole value into given function. After that one, this is their constant term. This is their value x z power of minus k minus 1. Z power of k minus 1. For this one, here we getting as like this. Here I am taking z plus 2 and z plus 2 square is cancelled and it is coming to as z power of k by z plus 1. Z plus 1. Limit z tends to infinity applied value. Limit z tends to minus 2 is the applied value. And here 1 by 1 factor is nothing but 1 value here. 1 by 1 factor is 1 value here. Okay. 1 by 1 factor is 1 here. So what are we getting here? Limit z tends to minus 2. Limit z tends to minus 2 at pole 2 no. At pole 2 minus 2 d by dz of it is coming as dk by z power of k by z plus 1. After that one, if you apply UV method, that is p equal to limit z tends to minus 2. Okay. U square, that is nothing but z plus 1 whole square into u into, okay, u by v, okay, v square by, so what is the formula for this one? All of you know, v square into v into u dash minus v u into v dash, okay, u by v method. So go for this one with here, okay, x plus 1 whole square into x plus 1 into, for this one derivative is k into z power of k minus 1 minus, okay, and it is constant, z plus 1 is constant. For this one z power k, it is coming to z power k. Okay, so substituting this one values here, limit z tends to minus 2 here in this way, we are getting the expression for this one. After calculation purpose, we are going to here k by 4 equal to minus 2 whole power of k minus k by 2 whole power of minus k. Okay, if we ask these two residues, that is for in first case it is R1 is here, okay, in second case it is here, first case it is second case, residue of 1 and residue of 2. This is a method for finding the residual method for inverse jet transform. If you want to cross check this one with the fraction fraction also, we are getting the same answer. Same answer. So what is the, in case of the fraction fraction, what is the equivalent of this one? What is the equivalent of this one? That is a by z plus 1 plus b by z plus 2 whole square plus c by z plus 2. C by z plus 2. This is a formation. Find the a and b and c values. Okay. Substitute that one into x of z and take the inverse Laplace transform. So we are getting the final answer. That is this value. We are getting this value. Same answer, this one. So now I am going to the one more method is long division method. Long division method. Where in case of the long division method, we are having the sequences, and that is x of z equal to n of z by d of z, where n of z value is going to be starting from b naught value, that is b naught to bm, and d of z is going to be started at 1 plus values. So first of all, in case of the long division method, first of all we have to divide the perform. We have to make it the value of the signal at the end installments. In installment samplets. That's why we are going. First of all, we see this one problem. Can you understand all of it? That is z by z plus 2 and z plus 1 into z plus 3. Okay. Just now we see this one problem in case of this one. Okay. This one. Just to see this one problem in case of residue method. Already I solved this problem in case of the fraction fraction method also. This is the answer. Okay. For this one, residual method, it is the answer. In fraction fraction, it is the answer. Okay. Same answer, same no? Residual method, fraction fraction method. Now, I am going for this problem in case of the long division method. Long division method. Okay. For long division method, just see this one. In long division method, first of all, they given as z square plus 2z by z square plus 2z by z square plus 4z plus 3. So this value I am taking here, and this value is I am taking here. Here. Okay. So we perform the same answer. Same divided method. First of all, in a problem, see here z square plus 4z plus 3 will be there. Here 1 minus z will be there. That is nothing but the first term is when is coming to 1. Here, if you multiply this one with respect to 1, what happened? If you multiply this one with respect to 1, z square plus 4z plus 3 value. Okay, z square plus 4z plus 3 value. Okay, if you multiply with this one with 1, so what happened? The first term is going to be 0. The first term is going to be 0. Again, see the value minus 2z and minus 3. If you want here minus 2z, there is nothing but minus 2z. Here you want to. So what happened to do? It is, that is 2 minus 2 power of z minus 1. Multiply this one. So finally we got the answer like this. We are getting answer. Okay, divide and rule. Just divide rule. Division method. So we got the answer. This one is, for this one we got the this value. These values. So what happened here? See, we know x of z equal to k equals 0 to infinity x of k into z power of minus k. Okay, if we expand this one, what happened? X of 0 plus x of z minus 1 plus x of z into z power of minus 2, like this we are going. Okay, so x of 0 equal to 1 answer. Okay, and x of 1 power of x power of 1 equal to minus 2. X of 2 equal to 5. If you substitute this one values. Okay, for example, see, it is a function now. X of z equal to 1 minus 2 power of z minus 1 plus 5 into z power of minus 2 minus 142 into 14 into z power of minus 3 minus, okay, 41 into z power of minus 4 minus 122 z power of minus 5. Put here x equal to, put here 0 value. Okay, z equal to 0 value. So what happened? 0, 0, it is coming. All are zeros, only 1 will be there. If you put here z equals 0, we are getting 1. Okay. Next, if you put here x equal to 1 in this one, in the above expression, that is 1 minus, okay, z equal to, what is the value? Z equal to minus 2. Substitute that one. If you substitute that one, if x equal to 1, you are substituting here, we are getting minus 2. If x equal to 2, you are substituting here, we are getting 5. Similarly, you are going. Okay. Now, I am taking all the values 1, minus 2, minus 5, minus 14, 41, up to here, 122 up to values. That is nothing but it is a x of k. It is a x of k. Okay. How can you say this one is x of k? That is nothing but here we are getting cross check this one. 0.5 into x power minus 1 into k plus 0.5 into 1 power of minus k. If you take minus k common, that is minus 1 into 0.1, 0.1. Okay. So it is solution for the same as for the partial fraction method value and previous method, that is residue method is also same. We got the same answer. Okay. Okay. Next, I'm going for next problem. Same as direct division rule. Here it is denominator value. It is numerator value. Apply division rule. We got the value as this value. Now I am going to writing this one x of z equal to, for this one, writing this one. For this one, what is the values of the integer values? That is 0, 1, 5, 11, 12, minus 13. Up to. Okay. Substitute this one values here. We get the answer values. Okay. Next one is, I am going to for distance value, divided rule value, long division rule value, it's same for formulas, but standard formulas. That is, if you write this one, z power of minus 1 plus 5 into z power of 2 plus 11 into z power of 3, direct this. So we get the value is, that is this one. Okay. So this is your direct division method. Okay. Now these topics I am taking in the form of in the textbook, that is Ogata textbook. I am taking that one, digital control system by Ogata. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.